Hi, everybody. Welcome. How's everybody feeling tonight? Hi. Phyllis, you're pointing me at the ceiling again. I can't see you.
I'm sorry, this is just mildly beyond my techno skills. I'm
Oh,
connected,
okay.
there's a...
You're there. I know you're there.
I'm there.
So, how's everybody feeling?
Good.
About glaze,
Say again?
about this glaze
Yeah.
stuff. I found myself that I have to listen to lecture like twice,
Mm-hmm.
understand, but I have time, so I'm doing it.
Do you feel like you're getting the information listening to it twice?
Again,
Do you feel like you're getting the information when you do listen to it a second time?
yeah, better.
Good. I mean, because you can even put it on, um, in the background, um, and just listen without the visuals. I mean, the visuals also help, but just if you want to be able to process stuff a little bit better.
Yeah, I have to make notes, so it's hard. Yeah.
Mm-hmm. Carrie, how are you feeling?
I'm good.
Oh, hold on, you're super quiet. Do you have
Okay.
There you go.
I just have this thing. They
That's
told
all
me
right.
my microphone wasn't working, but I guess if you can hear me, that's good.
I can hear you great when you turned it around.
Okay, cool. Yeah, it was kind of a overwhelming lecture, but
Today's lecture?
yeah.
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 Today especially is the mind blower. It's a ton of information, and it's sort of everything else propagates out from today's lecture. So I wouldn't be amazed, or I would encourage people to go back and review today's lecture once or twice, because yeah, it's a lot to discuss, and I have a feeling, depending on how many people have watched today's lecture, of that might be the topic of discussion for today. So, Dorothy, how are you feeling? Oh, you're frozen. Oh, are you there? No, Dorothy. Well, Phyllis, you feeling okay?
Yeah, actually, I'm fine so far. Yeah, it's not unclear. So it's not a good friend yet, but it's clear.
Well, it won't be a good friend yet. It'll take a while to get to that. So
Well,
does
that's
it?
all right. I
Yeah.
blew my son's mind by telling him of my incredulity that molecules had weight.
Oh.
I mean, knew they I knew they had weight, but I had never thought of them about weight, like
Wait.
gram weight.
Yeah,
So
absolutely.
that was interesting. So that was just an interesting revelation.
Well, it's those funny things that are always, that you need to sort of kick in, um, to be able to conceptualize it and in a very real manner. And for dealing with glazes, I mean, it's very much dealing with actual numbers of molecules. Just massive numbers of molecules, but actual molecules. So it's an important concept to wrap your head around. That I think, and as I mentioned, that was always the hard thing with chemistry in general for me, was not sort of having a realistic application. It was always sort of this abstract theoretical thing, and so to be able to have a real life application for it, I think, is really helpful. So, does anybody have any specific questions at this point?
Actually,
I have
Okay, go ahead.
sorry. I have one that goes back a few lectures, but it
Okay.
ties into what we're doing today. And it was when we were calculating the weight of those molecules, and then you had us divide one group by 100 and the other group by 500. Do you remember doing that?
Yep, absolutely. Let's see. I don't have that one open, so I have to open the lecture.
Yeah.
What's
Was
your question?
number? And Anyway, was there a reason that you used 100 for one group and 500 for the other group? I actually meant to ask that last week.
No, not particularly. It's just mathematical exercises to sort of see how it works out.
Okay, I mean, since they're all multiples of 10, I figured it was sort of a convenience thing, but I didn't want to miss something.
Nope.
Okay.
Scott, did you have a question?
Yeah, you talked. I got a couple of them.
Okay. That's fine.
When you talked to the ratios, the silica to alumina ratio, you had 10 to 1, 7 to 1, and then the gloss ends at 5 to 1.
Mm-hmm.
Is there any place in there where you can figure out the quality of the glass that you're forming?
What do you mean by the quality of the glass, I guess is my first
Well, one
question.
that would be resistant to leaching or something like that.
Great question. I'm just trying to debate about how much I want to talk about. So leaching is a topic that is going to come up extensively. Let me look. What day it'll come up. It's going to come up on, I think, next Wednesday. Looking at my schedule here. But we can talk about it a little bit here. So leaching is the ability of a material to withstand degradation. The ability to withstand attack from acids and bases, right? Which is where commonly glazes take a beating. So the fascinating thing that I have put a bunch of research in and we'll talk about next Wednesday is actually, yes, it is totally predictable based on UMF. Oh, hello. And the thing that makes it predictable actually has nothing to do with the silica or alumina. And this is something that took a lot of time and thought of wrapping my head around what the issue is. Because silicon and alumina are in everything, they're inescapable, right? That there is nothing about silicon and alumina that makes them more or less rugged as a material. They just are. Okay? The thing that affects the quality of the melt of that glass is the flux ratio.
Okay.
Dorothy, who was that? I know that person. Sorry. And so the flux ratio dictates performance. Now we talk about the 0.3 to 0.7, and I started to talk about alternative flux ratios. Is that Corey? Sorry, I know, I'm getting distracted. I'll keep quiet. Hi. You're muted. So the flux ratio.
There you go.
Sorry, Scott. We'll get back to it. Hi.
Hi, Matt.
How are you?
How are you?
Good. You're in Rochester?
I am.
Awesome.
We got a lot of your compadres here.
Yeah, there's a number of Alfredians here.
Uh-oh. Then there are probably stories about me that I don't want to hear.
No, only good stories.
Okay, good.
That I've heard so far. Maybe there's some other ones.
Yeah.
Well, you're talking to good people, so I'm protected, I guess.
I'm sorry for interrupting your lecture.
Oh,
It's good to
no,
see
that's
you.
all right. Okay. Going back to the lecture, though. Good to see you. Okay. So Skull was created with a set 0.3 to 0.7 flux ratio, and I talked about why that's so important, right? That it just goes back to history of that. That is where glazes worked really well. And you can trace that all the way back to the Chinese, okay? And again, this is some of what will come up next week. That just through trial and error, they found that 0.3 to 0.7 worked best, okay? And when you look at stuff like Seeger, when he used his cone formulas, he used 0.3 to 0.7. And it seems like this arbitrary representation. What we will talk about next week is when people started altering temperature, when they started talking about cone 6 especially, that what they started doing was altering the flux ratio. Okay? Because by adding more alkali metal flux, it's a more powerful flux. So it inherently melts at a lower temperature. Right? And I talked about that, I think, at the end of today's lecture.
Yeah.
Okay? So the problem with that is that alkali metals are very, very reactive. And what I have found through my research, what will come up next week, and what I'm going to be presenting at NCECA this year, is actually by altering that flux ratio is when glazes become physically and chemically weak.
Okay.
Okay? So, you know, like this tile I've shown a few times, or well, this is the better one. Okay? This is what happens when you have a 0.85 to 0.15 flux ratio.
Okay.
Okay, everything else should be fine, but the flux ratio is off, and it was etched by citric acid, by a lemon.
Uh-huh.
Okay, but that goes as far as 0.5 to 0.5. Those glazes that are 0.5 to 0.5 are actually the worst glazes you possibly can have, because you have just enough alkali metal in them to be making a weak glass, because they're not tied up in the glass structure. And so they are very susceptible to continuing reactions. And that's the whole reason why we use these alkali metal fluxes. Because they're so active, we need that activity. But we also need to keep it under control, right? It's that whole guy at the party metaphor, right? That we need to keep things going, but not go crazy. Because when you go crazy, the glaze is physically and chemically weak and is susceptible to leaching.
Okay.
Does that make sense?
Yeah. Now let me ask you this then.
Okay.
Because I told you I subscribe to Tony Hansen's Digital Fire, and I have a bunch of our studio glazes in that program. So I went through real quick and looked at them after I finished the lecture to see what the ratios were. And I found a couple of them. Where does zinc fall into that ratio?
It doesn't. Or I should never. Not that it doesn't. So this goes to a question. And actually, Phyllis and I were emailing about this over the last couple of days. Historically, the UMF is taught with this concept of limits, right? Where you had a certain limit of, you can have this much of one material and this much of another material, and they were these sort of random numbers that were put out there. And I think we were even talking about those last week, weren't we? So if you've got these limits that are out there, the problem is that the limits make absolutely no sense, to the degree that I won't even teach about them because they're so confusing. And a lot of what I have done in my research over the years is to throw away this concept of limits and to redefine it. Okay? And the thing that I have found is that 0.3 to 0.7 just applies across the board. It does not matter what flux is from the alkali metal or from the alkali earth that you choose. Okay? All that matters is that you've got 0.3 alkali metal and 0.7 alkali earth. Okay?
But now, does zinc fall under one of those?
Yep, it's an alkali earth.
Oh, it is. Okay, so it's, even though it's
in a different place on the periodic table, but if you go back, let me see if I can pull it up quickly. If you go back and look at pull up the periodic table, the ceramic periodic table. So this is really interesting. So I was having some issues with screen sharing on the clay class last night, but let's hope this works. Okay, can everybody see the periodic table?
No. Oh, there it is. There it is.
Yep, okay. So if you look at the periodic table here, let me expand this a little bit. And then, okay, so we've got this list here of modifiers, right? And that falls under these two columns here of lithium, sodium, potassium, and those are alkali metals. Then we move over to the alkali earths, and we've got magnesium, calcium, strontium, and barium. But this can actually be tweaked to include a few other materials. Now, under the classifications here, they're listed as intermediate modifiers. But number 1, zinc. Zinc is an RO flux. Number 2, lead, which we don't particularly talk about, but lead is also an RO flux.
Okay.
Number 3, iron. Iron is actually an RO flux.
Right.
And then the 4th one is manganese. Manganese is actually an RO flux, and I'm going to share something. I'm going to show you guys something here that is amazingly mind-blowing. At least it is to me because I'm a nerd. Hold on, let me find it. Sorry, I've just got to search through my documents. Okay, so this is some research that Grant Akiyama, who's one of our undergrads, did in my Glazes 2 class last spring. So we were discussing this notion of manganese as an RO flux. So what he went and did is he recreated Stull using only manganese as an RO flux. Okay? So he used, I got to go back up and look, I believe he used potassium and manganese. Okay? And this is what he got. A perfect recreation of Stull. He's got matte glazes over here. He's got glossy glazes in the middle. They dry out when you've got too much alumina and silica. It's amazing. It works perfectly when you just go, manganese is an RO flux, so I treat it as an RO flux. Okay? So I put it in a 0.3 to 0.7. I balance my flux ratio. I increase silica and alumina systemically, and it works perfectly. Like when we did this, it was so exciting because it works perfectly. Gloss, matte, all of it. You know, it's so cool that's how it applies. So the same thing applies to iron. The same thing applies to zinc, barium, strontium, calcium, magnesium. And it goes down to one of those things. There's a cruel trick, I think I mentioned in the lecture, but that I always play on my graduate students at the beginning of the year, where I put up a glaze formula with a ton of barium in it, and I say, what's this glaze going to look at? And I just give them the formula. And every single time, a graduate student says, oh, that's a matte glaze. Of course it's not. It's a gloss glaze. It's an exceptionally glossy glaze. But they all assume, oh, barium makes matte glazes, and there's a lot of barium, so it just has to be a matte glaze. But that rule no longer applies. We throw that out the window because what Stull tells us with this universal theory is that as long as you've got a 0.3 to 0.7, it makes no difference what those fluxes are. That Stull still applies.
Okay.
Matte, gloss, all of it. Okay, it's so cool. You look like you don't believe me.
No. I have another question then about the Stull graph that you had on the discussion today.
Okay.
Across the bottom was silica. Up the side, left side was alumina. And was it cone numbers across the top? Is that what the numbers were?
There are. Here, let me share it. Come on. Okay, so on Stull, across the top, there's various distinctions that just reference his numbering, don't really mean anything, and some of his labeling is antiquated. You know, what these particular S, T, and L, what those all mean are not particularly relevant. You know, what he's just throwing in lettering and all these types of things. You know, that it's just some of it is just his reference notes. That were published, but that the important parts are the semi-matte line, the matte line, and then this is listed as the devitrified line, but this isn't devitrified, it's actually underfired, so this should be unfused as well. And then the crazing region.
Yeah, it just looks across the top there. There's an axis, and it has 02, 01, and then 1, 2, 3, 4.
Right. those are just
kidding.
those are just graphic notes, as far as I know.
Oh, okay.
I've never seen anything in the literature to actually define what those are.
Oh, I thought maybe it was cone numbers.
No, because this is explicitly at cone 10. Actually, technically, this is at cone 11. But I reference it as cone 10 because it applies at cone 10, and cone 11 confuses people a little bit. But no, yeah. What's important here is alumina on this axis, silica on this axis, and the fluxes are set. So literally every single point here has exactly the same flux ratio. And that's the massively important concept, that the fluxes are set. And so this comes down to one of those basic concepts of, oh, I want to do this with my glaze, or this or that with my glaze. And as soon as I see anybody say, oh, well, change the feldspar, change the carbonate, my first reaction is to cringe, because that's the last thing you want to do. Okay? As soon as you start changing those parameters, you start changing the basic nature of the glaze, when in reality the basic nature of the glaze is set with the flux ratio.
Okay. Well, I thought each one of those dots within that graph was basically 1 mole of flux, and you were changing the amount of silica and alumina. Is that correct?
Correct.
Okay.
And inside that 1 mole of flux, you've got 0.3 moles of alkali metal and 0.7 moles of alkali earth.
Okay.
And every single point has 1 mole of flux tied to it.
Right.
And that goes back to Seeger, right?
Uh-huh.
Wherein that's the whole notion behind the UMF, as Seeger defined it, right? That we've got 1 mole of flux, and everything comes in proportion to that 1 mole of flux. Okay, so 1 mole of flux plus 0.1 alumina, 1 silica, makes cone 1, etc., onward into space. And again, that we can see that on this chart. Did it change? Are we looking at a stall with ratios? No.
It says the final system.
No. This is the problem. It's not letting me change slides. There we go. Okay. So now what we're seeing is that we can track Seeger's cones on the stall chart. This is literally cone 1. This is literally cone 2, 3, 4, 5, 6, 7. And again, if we could draw this map outwards into theoretical space, all the rest of the cones fall into that space as well. They're all there. It's just the cones are 1 mole of flux, a 10-to-1 silica to alumina ratio, and then incrementally increasing that by 0.1 alumina.
Okay.
Okay, so cone 42 is 4.2 moles of silica and 4.2 moles of alumina and 42 moles of silica.
Okay.
And cone 42 is a real cone.
So that the other chart that had the 0.3 to 0.7 with the cone chart.
Mm-hmm.
The one before this.
Yep, one sec. I got it. It's making me, the way the Hangout's working, it's making me go back and switch it back and forth. Okay.
So if I look at this, you have 1 silica, 1.1 alumina to the 0.3, 0.7.
Yep.
Now the next one is the flux staying the same, and then you're just doubling the silica and alumina, so the actual ratio of silica alumina to the flux is now double? Or are you increasing, does the flux also increase too?
No, the flux stays exactly the same.
Okay.
That's the whole thing that we do with UMF, of that every UMF calculation you have 1 mole of flux.
Okay.
And then you put silicon alumina in proportion to it.
Okay.
Now, I will go back and correct one thing, that you said that it doubles, and yes, technically from cone 1 to cone 2 it doubles because there's twice as much, but it's actually increasing by, it's keeping a 10-to-1 silica to alumina ratio, okay, because we've got 1 mole of silica and 0.1 mole of alumina. That's important, 10-to-1, but we're increasing each level by 0.1 alumina. Okay, so this is still 10-to-1 silica to alumina, but it's 0.1 alumina more than the previous cone. And then the next one is 0.1 alumina more, staying at a 10-to-1.
Okay, so well, no, you're not doubling. You're just adding 0.1 alumina each time, and the silica is whatever 10 times that number is.
Exactly. Whatever it takes to correspond to a 10-to-1.
Okay.
So I have to stop that. So again, going back to, the Stull chart, right? Because Stull, what's amazing about what Stull did is that he's not just sticking with 10-to-1, right? Where Seeger sort of left off is that he said, well, this is 10-to-1 and this is cones, and he just sort of left it there. And these cones are very real glazes, okay? You can take a cone 3, grind it up, and put it on the pot. It actually works. I've got a tile here somewhere on my desk. I don't know where it is.
Well,
I've got... Mm-hmm.
We use cones all the time in the kiln, and when they do come out, they are very glossy and nice. Now I know why.
Yeah, because they are literally glazes.
Yeah.
So like I said, cone 3, cone 4, cone 5, those make perfect cone 10 glazes because, as I mentioned, there's about a 6-cone range between when a glaze starts to melt and when a glaze is completely melted. And when we're melting a cone, we're just documenting something that is starting to melt. If it's completely melted, it's in a puddle, and that doesn't do us any good as a cone.
Right.
So that the composition of cone 3 actually makes a cone 10 glaze. Because at cone 3, this glaze is just starting to melt. At cone 10, it is completely melted.
Right.
Okay? And so that this is a radically important concept when we start to talk about temperature, which I mentioned at the end of this lecture. Okay? Because what this means is that, again, if we set our flux ratio at 0.3 to 0.7, which we should be doing for durability, and we'll get into that later, okay, that it also dictates temperature. It also corresponds to things that I say, like a running glaze is always an overfired glaze. Okay, now let's say you've got a glaze that tends to always run. I'll bet you dollars to donuts that it falls down in this region of Stull if you've got a cone 10 glaze that always runs. Why can I bet you that? Because this area has lower amounts of silicon alumina, so it inherently is supposed to be fired to a lower temperature. Now, maybe you like the fact that it runs and you've incorporated that into the glaze. Fine, I don't care. That doesn't bother me. But its actual firing temperature should be a cone or 2 lower.
Okay. But now you could try to correct that by adding silicon alumina?
Absolutely.
Okay.
You can add silicon alumina. You can fire it to a different temperature. Those are essentially the same thing. The cool thing that Stull tells us is if I've got a matte glaze, that's based on the chemistry. Okay? If you're under 5-to-1, it's going to be a matte glaze. Okay? Now, what that also means is that if I've got a particular glaze effect that I like, that is based on the silica to alumina ratio. But if it's running because it's too low of a temperature, all I have to do is increase the amounts of silicon alumina and keep the ratio the same, and I'll get the same performance at a slightly higher temperature. Okay? Because what Seeger tells us is that temperature equals chemistry. They are one in the same. So you can change temperature or you can change chemistry. As long as you do it systematically and correctly, it works perfectly. That's the entire notion behind cones. That's why cones exist.
Okay.
And that's what's so amazing about the UMF, because it suddenly gives us all the control in the world over temperature. Well, a lot of the control over temperature. I'll give you the rest as the class goes on.
Well, that's what I was just going to ask. I mean, do you maintain the same silica alumina ratio, just increase the amount of it, or is there some way that we're going to, let's see, or does everything within the formula also have to alter? I guess it doesn't. You
All
see
I
where
was, I see. I know exactly what you're saying, and I'm trying to figure out the best way to not answer you.
It's coming later.
It's coming. We'll get there.
Okay.
It's coming in a big way.
Okay.
Because yes, cone. This is the question. Then becomes, as you're asking, to fulfill your question that you're not asking, so everyone else can get the question. How does stall then apply to cone 6? If this is cone 10, how does stall apply to cone 6? And what I will say for tonight is it does, absolutely, and I will tell you how to do it, and we'll get there next week.
Well, actually, I'm thinking we have some glazes that do run, and
Okay.
I'm trying to think, well, do I just add a little bit more silicon alumina, get the same ratio of silicon alumina, and can I then maintain the basic glaze, but just keep it from running?
For the most part. Now, the one catch is some of the glazes that are down in that lower right-hand corner can be a little bit tricky, especially MAC glazes. Okay, because looking at the map. Oh shoot, that was the wrong slide. Hold on, I gotta stop and represent. Okay. That this map tells us one slight catch. If it's a glossy glaze, it doesn't matter. You're fine. If it's a matte glaze and you're down in this lower corner and you're running, can you increase the silicon alumina ratio and still get the same glaze? Not exactly. Okay, and that's because we have two different types of matte glaze. Down in the lower corner, okay, we have wollastonite-based matte glazes, and in the upper corner we have a northite-based matte glazes. This is for calcium. Whatever the specific crystal type is depends on what the RO flux is. Okay, so there's a limit to this sort of crystal A and crystal B, and it's around 0.3, 0.35. So if you have to increase your silicon alumina levels over that, that's when you're going to turn into a different type of matte glaze.
Okay. Well, this isn't actually a matte glaze. This is what we could call an amber celadon. It's a glossy glaze. It's beautiful, but it does tend to run.
Oh yeah, you just crank that baby up and it'll be fine.
Okay.
Now, you don't want to make huge steps. You want to make small steps.
Right.
Okay. 0.1 alumina increases, 0.2, or even 0.05 increases in alumina. Small steps, incremental steps. Make a couple of tests where you incrementally do that. And I find, actually, if you just want to do it blind, here's a good rule of. I hate to use the phrase rule of thumb. It's got a. I don't. Would anybody have a better phrase for rule of thumb? It's a terrible phrase if you know what it means. A general rule. If you're trying to keep the glaze performance the same, but you're not ready to do the UMF, by next week you guys will be comfortable to do the UMF part of it. But if you just want to just try something, if you add 1.5 parts clay for every 1 part silica, it should keep your ratio the same. Okay, so like 1.5% clay and 1% flint, and then 3% clay and 2% flint, and then 4.5 and 3%, and you do that systematically, that should pretty much keep you with the same flux ratio.
Let me ask you this: as far as that chart went with that before, if I increase the alumina 0.1, is that equivalent to raising it 1 cone?
Essentially, yes.
Okay.
Yeah, that's what Stahl teaches us.
So if I want to go 2 cones, then I want to go 0.2, and then adjust the silica to match that.
Mm-hmm.
Okay.
Now, although I keep saying that all this works perfectly, that glazes are still flexible. All glazes have a range. So if you just want to get something to not run, you may not have to go that far. But, yeah, that essentially, yes, that logically that works.
Okay.
And the same thing works. Oh, go ahead.
I'm sorry, from a practical aspect then, does the thickness of the application ever affect running? Which is
Yes. That's when gravity becomes an issue.
And
Thicker glaze applications will tend to run more. Thicker glaze applications also craze more.
And you mentioned that matte glazes could run. I've never had run into that. They always seem to stay put. Why would they run?
Am I in focus? Is this glaze in focus? Hold on, wait. I know what I can do. Ooh, I know what I can do. Wait. I've got my USB microscope. Hold on. I gotta change my camera. I don't know if I can get this in focus while I'm doing this. But let's see if this works. Oh, I gotta turn up the light. Oh, where's the switch? Hold on one second. Okay. Save. Now, are you going to let me focus? Hey! Turn down my light a little. Okay. So, this is a matte glaze. Okay, and then this is the bottom of the tile, which is completely and utterly run. Okay, and I've got... Oh man, I've got a lot of them here, actually. What's another good example? Here's a fun one. Okay, so this one, let me back it off a little bit. Let me see if I can get it better. I knew I got this thing for a reason. Okay, so here is a glaze that... Boy. Now, let's see. Okay, here's a glaze that is a very matte-looking glaze. And then as I scroll to the bottom of the tile, it's completely run. Still too bright. Off the bottom of the tile. Now, why can that happen? That happens because a true matte glaze is just crystals growing in a glass. Okay? Well, if the glass can run, then the crystals will run with it. Okay, because the glass is inherently viscous. Again, I know this isn't great. So, oops. Save. So again, that this is a fairly matte glaze, but you can see like it's completely run off the tile because the underlying glass ran, and then the crystals, they just precipitate out. In fact, a matte glaze that doesn't run is an issue because most likely it's not a true matte glaze. But we can talk about that later.
So when in Roy and Hesselbarth, they talk about cooling slowly from 1900 to 1500 to get the crystal formation to occur. Is that reasonably true? Or, on your theory of all mattes will always be mattes if they're truly well formulated, why would that matter?
I'm trying to figure out what I should say.
You're trying to be PC or correct?
Your words. A matte glaze is always going to be a matte glaze.
Mm-hmm.
In the cooling, you could dwell slowly. Now, you said from 1900 to what, to 1500?
In his or in their book, they describe that to get a matte to form, to allow the crystals to form in the matte glaze, that from 1900 to 1500 you should do, if you've got a kiln master, a ramp down of about 150 degrees an hour.
That's awfully cold.
What is cold? What his starting point is ending?
1900 to 1500. So that's cone 04 down.
Oh, sorry. This is well, you know
In
they do
F.
cone 6, so that's.
No, I know, but cone 6 is roughly 2200. I forget, somewhere in there. 2230, right. So you're already talking about 300 degrees under that to 600 degrees under that. Okay. Matte glazes, true matte glazes are crystals growing in a glass, right? So to make more crystals grow, you can dwell on the way down or slow cool on the way down. That is absolutely true. Okay? You know, I'm going to pull up something here. Hold on. Okay, so I was poking around Glazy the other day, and I came across this glaze, which I'm going to share with you guys. Okay, so here's this glaze from Glazy, right? And it is listed as Sherman Matte with Stain Edition at cone 6. Okay, here's the formula: Nephsi 35, Talc 15, Kaolin 15, Flint 15, Dolomite 10, 31, 24, 10, Mason Stain 5. So I then scroll down and look at the analysis. What am I seeing here that makes me uncomfortable? Anybody? It's in the big turquoise box.
That's too high to be a matte.
That is too high. Absolutely. That is too high to be a matte glaze. Because where we will get to next week is, I know that this is cone 6, which is throwing people off. Not to give away next week, but what I have discovered is that Stull applies at every temperature when done correctly. Okay? So what that means is that this is not a properly fired matte glaze. Okay? This is just an under-fired gloss. And that's the real trap with slow cooling versus, this versus that. Like, are you theoretically maybe growing a few crystals out of this glaze if you slow cool it? Yeah, sort of, but because Stull tells us that a true matte glaze is always a true matte glaze, that we know based on the chemistry. Now, my test is always, if you fire it a few cones hotter, is it going to continue to be a glossy glaze? So now I'm going to pull up a glaze here. Dorothy is left, but I'm going to show a glaze here from a student of mine, and is currently a teacher of Dorothy's. So it's probably best if she's not there. Student images. Okay. So these are pots by one of our grad students who graduated last year named Kelly Justice. Hold on, I'm still sharing it. Okay? And Kelly was my TA. And she came to me with this question of, she's got this. Now, why won't this screen share? There it is. Okay. Entire screen. Okay. So she came to me showing me this pot and said, hey, I've got this problem. This is a cone 6 matte glaze, but whenever I fire it hotter, it goes glossier. And to me, that set off red flags. Okay, because under this understanding, what we are learning here, a matte glaze is always a matte glaze. Firing it one cone hotter should not make it less matte or more glossy. It should just continue to be a matte glaze. It might run, okay, which is why running matte glazes are important, but it will still be a matte glaze. Okay? So when I went and looked at her chemistry, lo and behold, I found that she was just, now I'm freaking everybody out, that she was just making an under-fired glossy glaze. Okay, so what we did is we went back and tweaked her glaze to fall under 5-1, and we got this. Okay, and this is important because this is a true matte glaze. These are crystals growing in the glass, and we can tell because these little rivulets here is the glaze running just a little bit where it's thick. Okay, which is a really, really important concept because glass can run. An under-fired matte glaze is just an incomplete gloss. That can't run because there is inherently no glass, or at least not enough glass to run. Okay? And so these are incredibly, incredibly important concepts as far as glaze durability. Now, all of this as a way to go around of sort of saying, are they wrong? Yeah, they're wrong. Crystal growth can make a difference, but it depends on the glaze. Okay, and it's the same way that the limits are wrong, but it depends on the glaze.
Well, don't crystalline artists, don't they hold on the down firing? So how's that different?
Well, they are they are trying to grow huge crystals.
Right.
Which again, that you can make more crystals by down firing or cooling. Like I said, that is absolutely true. Okay, if you've got a true matte glaze and you down fire or you slow cool, yeah, you can grow more crystals or bigger crystals or any of those types of things. But if it's I'm trying to be nice here, you guys.
Right.
Is there another question so I can try to answer a different question?
Well, I was going to ask about Roy Hesselberth too, and how long have you been talking about them?
Just since before you came in.
And their book seems pretty strident as far as stability. They don't like the term food safe, but stability.
And I use similar concepts.
Yeah. So they seem pretty good, or they're pretty strict. What do you think?
I think.
I mean, yeah, I don't. I don't. You like to use the word slander. We don't want to slander anybody, but
No, I think of the books out there that theirs is very competent.
Yeah.
I think that there is a lot of good information in there. I think that they just don't have the complete picture.
Oh, another question I was going to ask is, no offense to them, but I think their glazes are kind of boring.
You said that, not me.
Right. You know, some of them are nice, but can you get really nice glazes at Cone 6?
Oh,
Exciting
yeah.
glazes.
Well, like that picture I just showed from Kelly. I mean, that you absolutely can.
Yeah.
You can get dynamic, true matte glazes. Okay. Again, this is not going to show you anything. You can't see anything, but I think I showed this last week. This tile in my hand is a true matte glaze at Cone 04. Okay? This is based purely on recreating Stull at Cone 04 under the right conditions. Okay? And I could try the microscope again. Let me see if the microscope will show the crystals. Hold on.
Well, you're working on that. How do you make your tiles? They don't look like they have an actual foot on them.
No, they don't.
Do you extrude them, or?
I make slabs.
Slabs.
And then I fire them. You know, actually what I do is the see, it's white on white, so it doesn't really show. It doesn't really show much. Yeah, it's impossible to image white on white. The traditional T-shaped test tile that people use, I actually just use to. Here we go. There's some crystals. So you see, these are all crystals growing in the glass base. And you can tell because they've sort of got a pattern to them. They're sort of forming these T shapes. And that's just a very regular precipitated crystal. And this was at cone 04. Okay? So I used that T-shape extruded tile actually as a prop for my flat tiles. So I actually just stand them up like this. Well, it would be like that.
Okay.
Right. I like a flat tile. I don't use texture. I know that that's a big deal for some people. It's just not. I don't know. It gets in the way of data, so I don't really use those. So okay, going back to glaze limits, why I don't like these. Okay, so this is from Digital Fire, right? And here are glaze limits. And this is sort of saying, oh, for green and copper at this temperature, you can have this much calcium and this much zinc and this much barium and this much magnesium and this much sodium, potassium, and this and this and this. And it's ludicrously complex. And it doesn't have any relevance to reality. Because even here at cone 10, right, this says, oh, well, you can have up to 0.7, you can have up to 0.8 for the UK traditional limits. What? You know, that there's just... It does not work this way. That there is no... Okay, he's saying you can only have 0.475 barium. Absolutely untrue. Absolutely untrue. You can have 0.7 barium, and it's perfectly glossy and it's perfectly durable. You can do glazes that are 1.0 barium if you want, depending on what conditions you want to use. That there are... This is all irrelevant. I mean, he even is just throwing out Stoll right here because at cone 10, you can only have 3.5 silica to 6.4 silica, wherever they got that from. It's just systematically untrue. It doesn't have any application in reality. You know, in this, and I don't mean to point out Digital Fire. I have no problem with Digital Fire. It's just that this is historically what is taught for UMF. That they take the concept of Stoll and they say, oh, yeah, that's fine for cone 10 or in theory, but, oh, I need this temperature. But what I'm saying is Stoll is gospel for every temperature, for every flux. Okay? We just have to learn the subtlety of reading it and then how to apply temperature, which is where we're going next week. Anybody not believe me?
Well, that's just supposed to figure out the same things for these different temperatures. Even just refresh my memory as to what those limits are for.
Though with the old limits?
Yeah.
And this is why I hate them, and this is why they will never come up in my lecture. They're only coming up in this discussion because the concept has come up. I honestly couldn't tell you why they exist, but it's the notion of if you want to glaze at this temperature, you can have this much calcium and this much zinc and this much this and this much that. And that those are supposed to be the applicable amounts. Right? But it's not true. It's not. And you know, that we've tested this over and over. Like before you came, Dennis, I showed a document. No, I've already closed it. But I showed a document from a student of mine who literally recreated Stoll using manganese as the RO flux, and it works perfectly. Hold on, I'll pull it up again. Because manganese is an RO flux. I just have to find it.
For some reason, I thought we started at 8:30, but it starts at 8, doesn't it?
8. Yep.
Yes, that's why I was late.
That's okay. Okay, so sorry for everybody who already saw this or is rewatching it, but just to share with Dennis, this is work Grant Akiyama, one of our undergrads, did with me last year, where this is Stoll. Okay, these are all just test tiles, and the two fluxes in this are potassium and manganese in the form of manganese dioxide. Okay, used to recreate Stoll. And what he got is a perfect recreation of Stahl. These are matte glazes. These are glossy glazes. At higher alumina levels, it dries out. At higher silica levels, it dries out. Okay, it is a perfect recreation of Stahl using potassium and manganese. This is why this is so exciting. If we'd never even heard of anyone thinking about this, much less actually executing it. But when he and I started talking about the fact that manganese is listed technically as an RO flux, we said, well, let's just try it. Because actually he was studying iron at the time, and iron is also an RO flux. Okay, this is what limits don't account for. That this works at all of these temperatures. And why were limits created? I don't know. It was just, I think it was people's attempt to try to rationalize the UMF. Come on, bring me in focus. Come on.
Were they just trying to simplify?
I think, you know, I think that Stahl was sort of abandoned and forgotten. Although one of my students in the clay class right now, who had previously taken the glaze class, sent me an article today from '88 from somebody who did reference Stahl. But I just don't think that they got it. And because Stahl is specifically listed at cone 10, like I said, my research that we'll talk about next week, where I started to take it and run with it, is to go, okay, we've got all these limits, and they're totally baffling. They make zero sense. Because the first thing that I did, I mean, just going back into my history, the whole way I started in any of this is when I was an undergrad, I was brought in by Dr. Carty from the engineering department. He and John Gill discovered Stahl in a book and said, hey, this is really cool. Why don't we recreate it? And they actually brought me in while I was an undergrad, and literally I spent a month during the summer making all those tests and recreating it, and it worked perfectly. And so we said, okay, well, this works, and this means that matte glazes are matte because of chemistry, and gloss glazes are gloss because of chemistry, and crazing happens because of chemistry. So then what's the implication of that? And literally my entire career has been following from that. When I first started teaching glaze calc, what we did is that we said, okay, wait. If Stahl works, and Stahl is potassium and calcium, but we know that we've got 3 alkali metals in at least 5 alkali earths, magnesium, calcium, strontium, barium, and zinc, what happens when you start mixing them? So instead of doing potassium and calcium, you do potassium and magnesium, you do potassium and barium, you do potassium and strontium. And they all work. Stahl just keeps recreating itself. Now what you get are different effects as to the kind of matte glaze you get, because different chemistry forms a different shape of crystal. Like I was just showing in that 04, that's got a T-shaped crystal. That's because of the chemistry of that crystal. Okay, when we come back to these images, hold on one second. Right, when we come back to these images, we are talking about 2 different shapes of crystal based on the chemistry. Right, that anorthite has this specific shape of crystal, and wollastonite has this specific shape of crystal. And we know this, that we can get matte glazes with different types of texture because they have grown different physical shapes of crystal in that glass. Then we can look at something like Val Cushing. Okay, Val loved to make glazes with dolomite. Matte glazes with dolomite. Why do you think Val liked to use matte glazes with dolomite?
It had both magnesium and calcium in it, so we got 2.
Ding! Ding,
Yes.
Phyllis! Ding!
Oh, good for me!
That's exactly right. So you get even more rich texture, more development of texture, because you're now forming 2 types of crystal within one glaze. And that leads to that classic Val Cushing matte texture, because the potassium, or the magnesium forms one crystal, and the calcium forms another. Okay, and so it comes out this way. Why are barium mattes thought as so wonderful? Because barium mattes are so buttery and so crystally because of the crystals that they form. Right? If we come down. Oh, it doesn't have it listed. And I always forget the names of the crystals because the phase diagrams are hard to define. But with barium, you form one, I believe, called slausonite. And it's the same physical, or it's the same chemical structure of crystal, but it makes a different physical shape. So it gives you that barium matte texture. But on the same time, when you recreate Stull with barium, you get the craziest gloss glazes. Okay, they're exceptionally glossy. And that's because of the molecular size of barium. It has less interference with the melt and gives you a glossier melt. And they're super glossy, super, super glossy. And again, so what I started doing with my students is we created Stull, and we created Stull, and we keep recreating Stull. Okay, because we are always finding new things, like Grant doing it with manganese, or doing it with iron, or doing it lead as an RO flux. Okay, that what we find is that Stull holds true no matter what the materials are. And then on top of it, we'll get into color. Stull actually dictates color. We talked about texture. Stull dictates texture. We talked about crazing a little bit. Stull dictates glaze fit. Okay. And it defines durability, as we were just talking about with Scott. All of these concepts are within Stull if you know what you're looking at. And I think that, again, that part of this is the research that I've done versus, what other people were doing as far as research versus the information that was passed along. And my whole thing was based on two sources. One, Carty and Gill getting me to recreate Stull, and then going, well, what are all the variables of this? And then two, looking at low temperature, because we figured out high temperature, we figured out Stull at cone 10 very quickly, and then the question became, well, how do we do different temperatures? Because if the UMF is going to be true, it has to apply at every temperature. This has to be a universal theory. And so what I started doing is looking at those limits, like I just showed you, and going, these make no sense. So what happens if I wipe this from our thinking and start fresh? And that's where we're going, of how we start fresh with chemistry and temperature. Because Seeger tells us that chemistry equals temperature. And what I have come to define solidifies this concept even farther. But we're not there yet.
Well, that's kind of the beauty of chemistry, isn't it? In the periodic table, it's just consistent.
It's completely, and if it's not consistent, then there's something wrong with the theory. And that's a discussion I got in with a very well-known ceramics technical person a couple of weeks ago on Facebook, where he said, oh, UMF is a really nice theory, but it doesn't work. And then he literally pulled up what I just pulled up of Digital Fire's UMF limits. And I said, yeah, limits don't work. The UMF works. That interpretation of the UMF doesn't work. But limits work. And I mean, I showed you guys last week that my presentation for NCECA this year is looking at this concept at cone 04. And it's still, the theory that I have come up with still applies at cone 04, still works. Durable, like I created glazes that are completely food safe and durable at cone 04 using the same concepts of temperature that we're going to talk about in the next week. Okay, I'm super jazzed about this. Like, can you tell? Like, this is what I love. Like, these are the things that, like, I'm so excited about. Because it's a complete reinterpretation of understanding temperature. And like this test came out of doing that. Sort of going, I know that this glaze is terrible. Can we define from Stull why this glaze is terrible? Spoiler alert, yes, we can. That's what my NCECA talk will be about this year.
In Portland?
No, in Kansas City.
Kansas City, yeah.
Portland's next year.
Is it?
Yes.
They went back to Portland before they went back to Minneapolis.
Yeah, no, they were only in Portland in, like, 2007?
Yeah.
Yeah.
Well, that's because it's Portland.
Everything got screwed up with New Orleans. When Katrina screwed up New Orleans,
Yeah.
it seemed like all the scheduling got screwed up. So I know I hope I'm not talking in too many circles, and now you guys are like, "What the hell is he talking about?" Because like he's really excited and going really fast, but like this is super. Like when I said that this lecture is a big deal. This lecture is a big deal.
Is that part of Glaze Doctors, or do you have your own lecture?
I do my own lectures. I don't do Glaze Doctors. No, this will just be me on the stage showing data about, shockingly enough, about Stull.
What it wasn't the last lecture, but the lecture before that, there was a slide that you really wanted us to remember, and it was about potassium versus sodium something. I don't remember what that was. Do you remember? I'll have to look through.
Was it the opacity? Because I don't remember either.
Okay, I'll watch it again.
I mean, the main thing to remember is, that you do get different opacity based on the RO flux, or the R2O flux, the alkali metal flux. And then the other thing is more of a clay problem, which is the don't put sodium in your clay body. Don't put sodium in your clay body.
Right.
If you make your own clay. Don't flux it with sodium. Don't flux it with Minspar. Don't flux it with Nefsi. Just don't do it. Bad habit. It's like smoking. It looks cool now, kids, but when you get older, you're gonna come to regret it. You're gonna get all addicted to it.
When I moved down here to Miami, it seems like a lot of times when I'm glazing, I almost have to glaze the inside of a pot one day and then glaze the outside the next day because of humidity.
But he's on bisque.
It's like it delaminates and crawls. Pardon me.
Is this on bisque?
Yeah.
Or on
bisque.
Wow.
Because if there's too much, that body the bisque is getting soaked with moisture and it just won't grab anymore. That's my theory. I'm not sure, but things were drier in Minnesota.
Oh yeah. Well, it's the same thing. If I went to grad school in Colorado, and my favorite thing to do in Colorado, where it's so dry all the time, and I was doing all slip cast wear that was fairly thin, I would cast stuff in the morning, and then I would have it in a bisque that night because the air was so dry, the relative humidity was so low, and then I'd do a very intense dry using oscillating fans that I could literally have something that was slip in the morning be in a bisque that night. And I did that many, many times. I've never worked with that high of a humidity. But yeah, I could believe that.
Especially if you're working thin. If your walls are thin, it's going to get saturated with moisture faster, right?
Right. Because glazes dry through capillary suction.
Right.
Okay? So as soon as those pores are full, they no longer have any suction. So if it's thin, if the relative humidity is high, you only get one application.
Right.
So you either have to wait, like you said, you have to wait for it to dry out, and it'll slide right off the pot. It'll look like a mudslide coming right off the pot. You're probably better off glazing the inside first.
Right.
Because that way at least you've got circulating air around the outside to dry that out. But yeah, I mean, unfortunately, keep an oven in your studio and hotbox stuff as you glaze it.
Right.
And that's just forcing the evaporation.
Right. I had a lot of that crawling. Yeah, it was just sliding, and it took me a while to maybe come up with a theory as to what was happening.
No, you're exactly right. It's all about that capillary action. It's the same thing with trying to dip glaze a pot that's been fired to temperature.
Right.
And they don't. In industry that they fire to high temperature and glaze to low, but literally when the pots are glazed, they go through a path of blow torches, which heat up the ware very hot, so that when the spray hits it, the water just evaporates instantly and it just sticks. It doesn't need the capillary suction, but it uses heat extraction through evaporation. But yeah, glaze thinner, less water. You could do less water and add a dispersant into your glaze.
Right.
But yeah, other than that, I don't really have a strategy. You could add CMC. That could help. CNC is a pretty basic binder. It's really just a tacky glue that, when it dries, makes things hard.
Yeah. Oh, go ahead, Scott.
No, go ahead.
Well, I was just going to ask about talc again, because we've got bags of talc sitting around from years ago, like 13, 14 bags of it, and it is Nital.
If nobody's taken it, you should steal it and put it in the back of a truck and drive it to me.
I'll ship it up. And then you were talking about Texas talc in the last lecture. And what about the Laguna talc? What is that?
I don't know anything about Laguna's talc.
Okay.
I mean, I don't know. I haven't used it. I don't know what it is. It might be from a different source. It might just be repackaged Texas talc.
Well, I just read that article in Clay Times, like last week. And
what did it say?
It was just telling about the lawsuit.
Oh, yeah.
It's supposed to be laced with asbestos. Right. And I just told my professor, so we're like quarantining the stuff, and now I find out after your lecture, that it's not true.
Yeah. And I got into a really nasty discussion with some people on Clay Buddies a couple weeks ago, where there were people going on about it. But it's literally, you have to understand the subtlety of how science works, how X-ray diffraction works, how these things are identified, and and then it comes down to the danger of exposure. And it's just it's not. It's just not the way it works. And it's fine. Nitalc is great. And again, well, the amazing thing that had happened in this discussion on Clay Buddies is somebody brought up, they submitted a document that they claimed made their point, but the document that they posted was literally a press release from a law firm that was trying to gain clients, talking about how great they were at suing for mesothelioma on talc. And it's like, no, they probably aren't. They're probably just getting the company to settle because that's what companies do.
Right.
And they always settle the deepest pockets. And it's amazing. There are things I can't go into now, but like experiences that I know people have where companies that are completely unrelated to issues get sued, and they'll pay because it's just easier to pay it and make it go away.
Yeah.
And I'm not saying that the mining companies are innocent. I'm not saying they're not doing evil things. It's just that what they got sued for, it's ridiculous. The things I know that you don't want to know. But, yes, from the school's perspective, they need to quarantine it.
Right.
The facts of the case are the company closed down.
Right.
They closed down the mine. The company still exists.
Right.
They no longer distribute that product. Now, the reality of the situation is that they did that for legal protection, to stop lawsuits from coming, because lawyers are voracious. Because they know that the chemistry falls in a gray area, that they can just do lawsuit after lawsuit after lawsuit. But the Nitalc is great, and the Texas talc, it's hydrophobic. It does not incorporate into water very well, and it has a lot of iron and titanium contamination, which changes color. It's just not great. Yeah. So I got to jump in. Grace, I see you there muted. Do you have any questions?
Oh, hello?
Hi.
Oh, hi. Can you hear me?
Yeah.
Yeah. Okay, so I have a question, not about glaze, though.
Okay.
About clay body. Because now I'm starting to doubt that Cone 6 clay body wouldn't work for my project. Because I'm in MFA program and I have a big show coming in June. I already started working on my final project. I'm making large jars, really large. It's about meter long. And then I'm trying to make 2 sets, and then 5, 6 will be stacked with each other. So I finished first set. I used cone 10 clay body. And then I fired in soda, and then people were telling me that you can just fire up to cone 6. So I fired cone 6, and then the 5 are stacked together perfectly. And now I bought cone 6 clay body, but then they're really, really heavy. And then you're talking about the different like temperature and then the strength. And now I'm wondering if I fire this clay body up to cone 6, they will, I don't know, be able to hold like few, I don't know, 1,000 pounds. Like that's
So you
my
said
concern.
that the cone 6 clay was really heavy. What do you mean by that?
The thickness and then the size of the work.
So you weren't able to build it as thin as you could before?
The first one, it was not the round shape. So, and then people, of course, around me told me that I put lots of grog. I mixed my own clay. So they said, it can go thicker, you know, because you're making big and then you're going to stack with each other, make it bigger. So I made it about inch thick. And then I put lots of, excuse me, lots of ribs inside. So it's even heavier. And now the second set I'm making using cone 6, and I'm trying to make it thinner than the first one and no ribs inside, but just size itself is really large. And then the total height will be about, I don't know, 2 feet.
So did the cone 10 clay work for you?
It worked, but I'm making more jars so that I can put on top of the set. So it will be even heavier. So my question is, the bottom piece would be able to hold the weight and then will not break during the exhibition? Or should I just fire it up to cone 10 and then use cone 10 clay body? Does the temperature like affects on the strength of the clay body?
Yes, absolutely. It does. It's a big subject for another time. The problem is cone 6 clays are made to have a different fired standard than cone 10 clays. Okay, they're just not made to be as rugged when they're fired. Now, when you're making something so big, could that be an issue? Yes.
Like the interesting firing I just had was like a month ago. I fired soda cone 6, and it was my big test kiln. And I tested 6, 7 different clay bodies, half cone 6, half cone 10, and fired up to cone 6. But then I was cooling really fast, and I was opening the kiln when it was about 500 Celsius.
Okay, and what happened?
Of course, many pots exploded and then cracked or broke down. But the thing is, all about the cone 10 clay body, they survived. And then I have 7, 8 pots that were broken, but they were all made with same clay body, cone 6, with manganese in it. So
and you're saying those all died?
Yes, not all died, but the pots, the broken pots were all made with the same clay body.
Right.
Cone 6, black.
So the thing is, and this comes to the inherent problem with cone 6. Why I'm not a fan of it. Honestly, I would say go to the cone 10 clay. Because it sounds to me like you made all this clay yourself, or you said you bought the cone 6 clay?
Now I'm using just commercial. I bought the boxes of clay.
Because you don't know what's in it, I would guess that you got dunting. The cracking you got is called dunting. Okay, and it happens because in the soda firing, did you glaze the inside of the pot?
Some I did, some I didn't.
Did you notice any correlation between that with the cracking?
I think most of the, no, not all the pots that were broken, I think I glazed them.
They were glazed. That's what I would expect. So when a clay is when they do this thing to change the chemistry of a fired clay body, all they do is that they lower the standard of what they're calling well fired. Okay, so clay and glazes all have thermal expansion. They expand and contract when they heat and cool. And if you have a pot that is under-fired, especially with the way that they have cone 6, which actually that cone 6 clay could be even more under-fired than the cone 10 clay fired to cone 6. I know, you're laughing, Dennis, but it's true. Okay? When you combine that with a glaze on the inside, the glaze cracks on the firing, and then that cracks the under-fired clay body. And that's called dunting. Okay? Now, you can overcome this by a few things. One is using a different clay. Sometimes glazing the outside with the same glaze as the inside of the pot will help, but since you're doing soda firing, that actually is probably going to make it worse. Because that soda forms a glaze on the outside of the pot, which has its own thermal expansion, which is going to react in a completely different way. And it's going to react randomly based on the firing and the soda application therein. Was there a reason the people around you gave you for changing the temperature, except that, oh, you could do it?
Well, because my pots were so, like my jars are so big, and the first one that I built, I fired it in soda, and then it survived during the bisque firing. But the second firing, I found crack. So I was filling it with epoxy putty, fixing it. But then people are saying that you're giving that, I don't know, piece too much stress, and it's not functional pot. So why don't you just fire up to cone 6, and then it's gonna work? I don't know, it work. That's why. And then people keep saying the cone 6 is hot enough. It's high firing. So it shouldn't matter, like cone 6, cone 10. And I keep asking, but those jars are really large, and then they will be stacked with each other. So the bottom piece should be or has to be able to hold the whole weight. Is it going to be strong enough? And they say, I don't know, it shouldn't be a problem. The cone 6 and cone 10, it doesn't have that much difference. So yeah, that's why they keep saying you don't have to go up to cone 10. It's just, yeah. And now I'm doubting.
Well, I think, you know, do you have a lot of history building these large jars? I mean, I see in your picture you've got a large pot piece there.
Because I make ongi jars, the fermenting jars. That's why I wanted to bring this. Yeah.
You know, yeah, you can make, I mean, so if you're familiar with ongi, I mean, you know, do you build around a drying pot? You probably can't in your studio.
Excuse me, sorry?
Like a drying pot, like oh god, what's his name? We've had an ongi potter come to Alfred several times, and I'm just blanking on his name.
You mean a Korean or?
Yeah, Korean. I'm so terrible with names, but nonetheless, when he works, he literally has a bucket hanging from the ceiling that has a fire going in it.
Yeah, the coal, yes.
Yeah, and that is drying out the inside of the pot. And actually, this is the same problem that we were just talking about with Dennis, but from a drying perspective. But it's made to dry the inside of that pot from the inside, because you don't get air circulation through the inside, and if it doesn't dry evenly, you'll get cracking. So, I mean, ongi's got a huge tradition of that. But this same potter, God, I'm killing myself. I remember his name when we were out of class. I've given him porcelain, and he's built ongi out of porcelain. Now, obviously, he's a master potter with a lot of experience, but, you know, the clay, you can do it with any clay as long as the clay is really good. I would probably stick with cone 10. I think if you're, you know, if you had more time and we're going to be developing a clay body and this, that, and the other, but I would stick with cone 10 if I were you. I mean, all the things that, oh, you can do this, you can do that. Yeah, you can. You can go dance out in traffic. That doesn't mean you necessarily should.
But I'm kind of confused because I got my BFA in Korea. Then I'm a big fan of like not Celadon but Buncheonwear. So anyway, so I never used Con6 clay body in Korea. But all of a sudden here, it's kind of a big trend, and I feel like I have a kind of assumption or from people that Con10 is kind of wasting of fuel or time or stressing kiln. So I'm confused. Like really? Like,
Grace, maybe you can defend your cone 10 position with the fact that the cone 10 pots survived in this last firing, and the cone 6 pots did not survive. So it proves to whoever's saying cone 6 that cone 10 is stronger, and you can defend yourself that way.
Where are you at school, Grace?
I go to University of Manitoba in Winnipeg, Canada.
I don't know. Who's your faculty?
I mean professor?
Yeah.
I have Grace Nickel. She's my advisor, and she's the only ceramic professor here.
I don't know her. I was just trying to figure out if it was somebody who I know so that I could say.
Stephen Grimmer up there?
Yeah, I had Steve Grimmer, but he left. Yeah, he left a year ago. So.
You have my okay. Go back to Cone 10.
Thank you.
And you can tell this video will be on YouTube. We are currently about an hour and a half in. You can tell your teacher, I give you okay to go back to Cone 10. You're absolutely right that Americans, and I don't know if it's just Americans, have this obsession with Cone 6. But it's so frustrating. This is my life in both the clay and glazes, is dealing with the mess that was made by making Cone 6 a thing by a bunch of people that don't actually understand the chemistry of Cone 6 in both clay and glazes. And the fact is that Cone 10 works better. There are less inherent issues with Cone 10 because it's established practice. Like I said, next week as we go, we'll talk about in glazes how to make Cone 6 work. I just showed you with those Kelly Justice pots of how to make beautiful, diverse matte glazes at Cone 6. In the clays class that I do, we're talking about how you can make clays that work at Cone 6. It's perfectly reasonable. But if you're stuck with commercial, if you don't have a lot of time to test and develop your own clay body, which, I mean, even if you're talking about a show that's 6 months away, you don't. I mean, you just don't.
No, I don't.
So I'm giving you the okay. Go back to Cone 10. This, unfortunately, you know, that the notion of, oh, well, you could go to Cone 6, so you should. Honestly, sorry, teacher, if you do end up watching this, that's not good advice. Okay? You don't save that much energy, and you get a massive amount of technical problems. Okay, and yeah, I mean, Dennis, you're shaking your head because you're saying you went down to Miami and everything's Cone 6 and you see the same thing.
And she doesn't have time to perfect it.
No.
And temperature.
No. You can. It can be done. But not in the next 6 months.
Right.
Not even the next 6 months. I mean, you got to make these pots now so that they can dry and fire.
Yes.
Go to Cone 10. So you're getting Plainsman clays?
I'm sorry?
You're using Plainsman clays?
Plainsman and Laguna B3 brown.
Yeah.
That was the problem.
The Laguna clay?
Yes. There was the pots that all broke.
Yeah. Just go to Cone 10. Don't even, yeah. I mean, I hate to give you such a pat answer because there is a better answer out there. You just don't have the time for it now.
Okay.
Do it works.
I agree. Thank you.
And like I said, you can tell your teacher. This will be on YouTube. Tell him to watch it about an hour and a half in. Sorry, teacher. I don't know you. I'm sure you're a wonderful person, but Cone 6 is not the right one. Yeah, she can take my class and learn why. Anyway, any other questions?
Yeah, when are you going to write that book, Matt?
It's coming.
There's a painting professor, an old timer down here, who's thinking about writing a book.
About glazes?
No. About abstract expressionism. Yeah. Mm-hmm.
I'm working.
It's kind of intimidating, isn't it? A big project to write a book.
It's not even that it's intimidating. It's that I'm busy.
Right.
In between, like I said, so I don't know whether you're here, as I was mentioning that my whole deal is I don't actually live in Alfred anymore. I live outside of Gettysburg, Pennsylvania.
Oh, you just said that. Yeah,
no, I know.
I was wondering. Yeah, Gettysburg.
Yeah. My wife is a ceramic engineer, and she works for Dahl Tile. And she used to run a tile factory near Alfred, and then she got recruited by this big company, so we moved down to Gettysburg. And that's sort of where the online teaching came, is that obviously I'm still associated with Alfred, but I don't live there anymore. And so my actual job is that I am now a stay-at-home dad. So I've got the 2 kids, the 3-month-old baby right now. So I'm taking care of them on top of doing consulting work and doing research and teaching. And so like this term, I've got my Glaze class, which is new, so all my time's going into that. And then this spring, I'll be teaching my Glazes 2 class online to AU students, which will be another new class. So it's just all this time putting into developing an online curriculum. And then once that's done, then I can write my book, once my kids are raised.
Yeah, right.
I can hear the 4-year-old giggling upstairs, who is supposed to be in bed.
Matt, can I ask a question?
Absolutely.
You, in the lecture, I think it was today, you talked about when you fire and you get to temperature, you let it soak for a while. I thought it was like a half an hour or an hour or something.
Yeah. Uh-oh. Are you about to expose me?
Well, no. It's just the whole heat soak thing and whatever. I fire everything cone 10. We have reduction kilns, and I like doing everything there. But we do have a small group that likes to do cone 6, and they're using the cone 10 clay, but they're using cone 6 glazes. And they usually let it soak. They get it up to cone 6 and then soak for like 10 minutes. Well, somebody who's not usually programming the kiln, 2 of them loaded the kiln, and she said, well, I know we always let it soak, so they put a 2-hour soak in. The glazes ran like water.
Yeah.
I was kind of surprised to hear you say you let yours soak as long as you do.
Yeah, well, you are exposing me because it does actually equal a higher temperature. Okay, because, again, this is sort of what today's talk comes out as, is that chemistry equals temperature. Time also equals temperature. And actually, if you go and look at, I can pull one up here if I can find it. If you look at Orton's cone chart, they very specifically say that your temperature is based on
a certain climb rate,
a certain ramp rate. Now, here's the thing of that. This is all, so here's Orton's cone chart, and I can zoom in. That this is specifically saying that these temperatures, so you pick a cone, is based on the ramp rate. But if you look closely, it also says degrees C per last 100 degrees C of firing. Okay, so that's the second caveat. It's only the last 100 degrees, technically, that this applies, which is a questionable concept. But that there is a correlation between time and temperature. Well, this is actually cool for a couple of reasons. So we were talking about the matte glazes a little while ago. The matte glazes will still stay matte even though you fire them with a soak at the top, not on the way down, a soak at the top, because they're still going to precipitate out as they cool. That's just the chemistry of the system, that those crystals need to find stability, so they precipitate out. I do it because I don't believe in the consistency of our kilns. Okay, I mean we were just talking about this last week about the lack of consistent temperatures or getting a hot wall or any of these types of things.
Right.
Because our kilns need to homogenize. It's the same reason why I don't recommend firing to a kiln sitter, because a sitter, that cone melts and it just shuts off. And sitters, at the end of the day, are really just supposed to be used for emergency purposes. And so if you're firing to cone 10, you should be putting like a cone 12 sitter in there just as an, oh crap, I wasn't paying attention and it overfired, shut it down. Okay, but if you fire to a temperature, as soon as that sitter hits 10, that sitter is sitting right next to the heating elements. Okay, but it says nothing about the center of that kiln where the heat really needs to be. It says nothing about top to bottom and side to side.
Yeah.
And so, I mean, I like a soak. I used to do it for an hour. I backed off. 10 minutes is fine. 30 minutes is better. It does technically equal a higher temperature. And actually, Dr. Carty in NSECA in Seattle posted some research that he's been doing about Korean pots and long-term firings, and sort of reverse engineering how long their firings were based on looking at how the glaze was actually dissolving the clay body. And he was determining that they would do these ultra-long firings, so they would only be firing to cone 8, but it would actually be the equivalent of cone 10 by just having longer soaks at temperature. Yeah. Because chemistry equals temperature, time equals temperature, everything equals temperature. So it is this very interesting, flexible relationship back and forth.
Yeah, I was just curious to see why you went quite that long. I can understand why the soak. I just was kind of surprised when you said that long.
Yeah, it probably gives you realistically about a cone, but I'm much more interested in getting homogenized heat.
Yeah. Well, I can understand that, and especially in electric kiln.
Yeah.
In a forced air, gas kiln, I think things probably tend to stay a little bit better because you've got a good draft going through there.
Yeah, you've got a good draft that keeps it pretty consistent. The refractory tends to be thicker, which will retain heat better. Uh-huh. I mean, I don't remember whether I've ranted at you guys about the electric kilns yet, but just the way that those walls are so thin, they're just dumping heat out those walls.
Oh, I've seen them when they shut off, and the temperature just drops like a rock.
Yeah, because 2.5 inches of fire brick is radically insubstantial. That those boxes, they're just dumping heat the whole way up. And so if you've got a gas kiln, most likely you've got 9 inches of brick or fiber or whatever that is retaining that heat, so the heat is inherently homogenized. In a barrel electric kiln, those elements are constantly dumping in heat, just trying to make up for the heat lost through the walls.
Right.
Much less the amount of heat that they then need to put out to increase the temperature. I mean, it's all part of my Cone 6 conspiracy, which is the book I'm going to write someday. The Cone 6 conspiracy, because clays, glazes, and kilns, they're all being done wrong at Cone 6.
Okay.
I know, I'm a crazy person. I have my reasons.
That's right.
They're crazy reasons, but they're true. Just because I'm paranoid doesn't mean they're not out to get me. Anybody else got any other questions? Have I rambled enough? Phyllis, you're good for now?
For the moment.
Okay. Fred, are you good?
Yeah, okay.
Okay. All right. Any other questions, folks?
Maybe I have about the lab that you say something about the lab to take out the. So I'm using Cone 6 glaze, and I have the frit.
Mm-hmm.
And what I'm doing with the frit, I leave it there. I want to try to change, let's say, the roaster knife and other stuff.
Which lab are you on?
The second one.
You're on the second one. Okay.
I don't have it in front of me, so I really.
1 second. I gotta pull it up. Where did I put it? Oh, there it is. Okay. Okay, so with the frit, just leave that as is.
Okay.
Okay, because you don't have a substitute for what the frit is besides another frit.
Okay.
Does that make sense?
Fine.
But keep it consistent through all of the tests.
Yeah. Okay. That's right.
And actually, that should have some fun results. Anybody else? Alrighty, folks. Okay, so everybody have a safe New Year. Don't drive. We were just talking about my wife wants to go to bed at 7:30 tomorrow. Hey, we've got 2 kids. What are you going to do? No, what you find out is that I think it's Netflix this year has announced that they have a ball drop video, so you just play it whenever and you tell the kids it's midnight and send them to bed. We did that a few years ago. A friend of mine found a web feed from, I think it was from England, so we just did it at 7 p.m. with the kids. It works. Okay, folks. Well, I will see you next week. Enjoy. Yeah, like I said, for next Wednesdays, we'll start to talk about temperature, which we talked about at the end of today's lecture. But this is now that we've gotten through Seeger install, this is where things get a lot of fun. Like this is where I'll blow your mind. I promise.
Sounds good.
Good. Okay.
Thank you.
Thanks, Matt.
See you guys later.
Yep.
Good night.
Yeah.